Okay, welcome back to part two. What you see on the screen now is the test software. TEST stands for the Expert System for Thermodynamics. This is the opening screen after you have logged in. If you successfully log in, then you'll see a greeting here for you and how long your license is valid for. The test has a lot of information in it. I recommend that you just go through and take a look at everything that's there. Today, what we are going to look at is we want to solve that one steady flow problem using steam. And so in order to determine which of the applications, we go into this bottom tab that's called Test Apps. Click on that. And now you have the map of all of the applications that are useful in thermodynamic calculations. As you'll hear me say multiple times during the semester, to solve a thermodynamic problem, one has to ask the question or look at the three letters SSP. The first letter S stands for system, whether it's an open or a closed system. Again, Professor Tran should have talked to you about the differences between the two. As you can see here in this flow diagram, if one has a closed system, such as a gas in a piston cylinder arrangement, you would then specify a closed system. If one had an open system, such as a gas turbine or something where fluid flows in and flows out, one would select open system. The second letter of SSP stands for substance. And in this particular case, our substance is going to be steam or water in the vapor slash condensed state, depending on where it is with respect to the dome. Our third letter is process, P. And process basically ties then everything together and allows us to actually solve the problem. In the problem at hand, we have a steady flow through a turbine. The fluid is steam. In the process, one of the process is that it is steady state, no time dependency, it's building up over time. Also, as stated in the problem, it's an adiabatic process. And adiabatic means that there's no heat transfer. And so with that in mind, we will then be able to solve the problem at hand. And so for that particular problem, you'll notice that we'll go down through the open system. And again, it's a steady process as opposed to an unsteady process. And in this particular case, most of the open system steady problems will be single flow system. There's only a single fluid that's passing through. You'll notice that when I hover over the single flow, you'll see a picture show up, and it looks like a compressor, or it could be a turbine, depending on what everything looks like. You'll see in here the description. It could be turbines, compressors, pumps, nozzles, diffusers, throttling valves, and so on. And so we will select that. Here's where we then answer the question, what is the substance? And the substance that we can pick from, we can assume it's a gas. And when we assume it's a gas, we may have three different forms of gas that we'll talk about: a perfect gas model, an ideal gas model, as well as a real gas model. We could possibly have a mixture of gases, and we'll talk about that later on in our class. And then we also will have the possibility of it being what's called a phase change. Phase change, as you can see here, there is the dome, and the fluid could either be or could reside in the vapor phase, it could reside in the two-phase region under the dome, or it could reside in the liquid phase on the left side of the dome. So since we're dealing with steam, which is water, we will select that as our substance. You'll notice that once I've selected that, we've identified that it is an open, steady process, single flow. It is a phase change type of fluid. You'll notice that there are some examples that you can go and look at. There's discussion of the various apps. And what we're wanting to do is then to go into the app itself, the phase change test app. And once we do this, then you'll see that we get in a page, and the page then allows us to identify and to specify the states of the substance. Anytime one of these types of panels is presented, we always take a look at what is in yellow, because that's something that we may want to change right away. It defaults to water, so it's defaulting to water as a possible multi-state type of substance. We also defaults to state 1. In this particular problem, we're going to have state 1 and state 2. State 1 will be the input, state 2 will be the output. And so once we then specify, you'll notice that of the various states, the velocity and the height, or the position, the data from the datum, are also specified in green. Anything with 0 velocity and 0 height. Now this velocity we will be changing a little bit later, because we have to have a velocity for the fluid to pass through. And so I'm going to turn that off because we will specify what that's going to be. What do we know about the problem? We know from the statement of the problem that the pressure was given, as well as the temperature for the incoming state. And so in order to put in the pressure, one just can specify the units. And in this case, the pressure for that particular problem, if I go back to the blackboard, or excuse me, go back to that, we see that it was 6 megapascals and 530 Celsius. And so 6 megapascals, type in 6, return, and the temperature was in Celsius. Okay, it defaults to Celsius, and the temperature was 530. Okay, let's go back and take a look, and yes, indeed, it was 530 Celsius and 6 megapascal. Exiting, though, at a 2.5 and 420. What we also know is the mass flow rate of 0.127. And so knowing that, we come back and we notice that there is an area to put in the mass flow of 0.127. Okay, so by putting in the mass flow, putting in the two thermodynamic properties, the two independent thermodynamic properties, it was able to immediately determine that it was superheated. And the density, the specific volume, the internal energy, the enthalpy, the entropy are all calculated. Okay, we no longer have to determine what state it is in. We don't have to go to a superheated table and look at to determine whether or not it's superheated. It already is determining that for us. And so in this particular problem, we put in the mass flow rate. And what I'm going to do for this particular problem is I'm going to just make an assumption that the area is just 1. Okay, because all we're really looking for is what is the area ratio from the input to the output if the velocity stays the same. And so in this particular problem, if I just say the area is 1 meter square, it calculates what the velocity has to be, because of the fact that it knows the m dot, it knows the density, it knows all the thermodynamic properties. the initial state determined. We now are interested then in going to the second state. And so we have to ask ourselves, what do we know? It's still water, so we don't have to change that. We go back and we see that the pressure is 2.5 and the temperature is 420. So I come back here and in megapascals, the pressure is 2.5 and the temperature is 420. Again, that's 420 Celsius. You'll notice that it's Celsius right there. Okay. And what have I done wrong? Let me turn that off. Okay, let me put that back in. Okay. So again, green means good. So if anything happens and it doesn't turn green, just delete it and go back. So because these two thermodynamic properties are specified, all the other thermodynamic properties are determined. We know that it's a steady flow process, and so we can put in the same m dot at the exit. We don't have to actually know or put in the number that was there before. We can use the variable m dot 1 because it's the same. So m dot 1 is equal to m dot 2. And so we have specified by doing that it's a steady process. What else? Well, we want to turn off the velocity here. And with the m dot known, okay, now the area and the velocity, okay, will be calculated. If I come back, since I turned off the velocity, I'm now going to recalculate. And because I have specified the value of my we were told in the problem that the final velocity is the same as the initial velocity. So one needs to read the problem carefully and decipher as much information out of the problem as you can. And so again, the problem stated that it was, we were looking for the ratio of the exit area to the inlet area to keep the exit velocity equal to the inlet velocity. And so that's key to solving the problem, as is the fact that it's steady, which means that the mass flow rate stays the same. And what happened was the pressure temperature and the pressure temperature are known. And so we can then go back. And so we have the answer to the second part. And the answer to the second part is that whenever the area is 1, area 1 is equal to 1, area 2 is 209. So 2.09 is the ratio of the exit area to the entrance area for a constant velocity from inlet to exit. Okay, so we now have to determine how much work was actually done. We have state 1, we have state 2. And so after determining these two states, we then can go directly to the device panel. And the device panel, you can see here, we have an inlet and we have an outlet. And for the inlet, we can say that that's coming in as state 1, and the outlet is coming out at state 1. Now, what do we know about the process? Well, we know that it is adiabatic. And what adiabatic means is no heat transfer. And so we say no heat transfer by actually specifying that Q dot 1 into device 1 is equal to 0. Upon doing that, the equations, the mass continuity, the energy conservation, and the entropy equation are all solved. And we can then determine that the output is 26.58. So 26.58 is the kilowatt of power that is generated through this turbine as the fluid expands. And we know that a turbine generates work out of the system, which is a positive number. And so we've solved the problem. Now we need to figure out how to get to the information that we need to present to me, the teacher, to be graded. So The next step is to go to the I/O panel and just do what's called a super calculate. And upon doing a super calculate, what happens is you see that all of the input, this is the input area, you see that it tells you what you put in for the various states. It also tells you what you did for the devices. And with that information, it then generated the output. And the output was, this is the magnitude of the work being done. And again, the ratio of the two areas would be obtained from the two areas associated with this particular system. So we had assigned this area A1 as 1, and area 2 then was calculated down here as 2.094. And so in the next video, I'll show you how you go about taking this information, putting it into the Word file, cutting and pasting it into the Word file so that you can upload it as a PDF.